Thank you to Brilliant.org for supporting PBS. Life as we know it is carbon-based, but does it have to be that way? There is another element on the periodic table that shares some of the key properties of carbon, but is far more abundant on most planets. I'm talking about silicon. So could there be silicon-based life out there? All of the chemical machinery of life, all biochemistry is based around the carbon atom, at least as far as we know. If we want to understand the possible diversity and abundance of life in the universe, we need to ask whether this is the only option. Perhaps the most popular alternative, at least in science fiction, is silicon-based life. We have the xenomorphs of the Alien series, to the giant space worm in Star Wars, and many, many others. So why are sci-fi writers so into silicon-based life? Because it really is the most promising non-carbon prospect due to its chemical similarity. It's also more abundant on Earth than carbon. So can life be based on silicon, and if so, why aren't we silicon-based? When we say life is carbon-based, we don't just mean that life uses carbon a lot. We mean that literally every aspect of the molecular machinery that makes up life is based around the chemistry of carbon. Carbon chains and rings form the scaffolding for an enormous variety of molecules which enable the raw machinery of life, from DNA and RNA to amino acids and proteins to all the structures built by these. Biochemistry is by definition the chemistry of carbon. In fact, biochemists don't even write carbon in their formulae, they just draw bent lines and they know that that's supposed to be a carbon atom. So why is carbon so favoured by life? Is it just that the first life form happened to be carbon-based, so everything else got stuck with that atom? Or is carbon-based chemistry really the only way that life can happen, anywhere, ever? Ultimately, carbon's incredible utility comes down to the way it bonds with other elements, which enable the right balance of reactivity and stability. To understand this, we need to think about energy. Nature will always try to get to the lowest energy state that it possibly can. A stick of dynamite, for example, is in a high energy state due to all of the energy stored in the chemical bonds of its nitroglycerin molecules. If the atoms of this molecule find a way to a lower energy state, they'll go for it, explosively releasing all of that energy in the process of converting the nitro into smaller molecules. Nitroglycerin is unstable because it only takes a little energy to break its tenuous bonds, which in turn releases a lot more energy than went in, initiating a chain reaction. That reaction only goes in one direction because it's not energetically favourable to reassemble all the smaller molecules back into the nitro. Life is basically an ongoing chemical reaction. You don't want the chemistry of life to be unidirectional. You don't want all of the raw ingredients to end up in the same overly stable molecules with no way back. That means the reaction is over, which for life means, well, death. At the same time, you want the molecules doing the work of life to be stable enough. They need to last long enough to do their jobs. In other words, you want a balance of reactivity and stability. Let's figure out what elements might be good for reaching this balance. And to start, we're going to open up the entire periodic table to see what we can rule out. The key is in what types of chemical bonds a given element can make. There are three main bond types: ionic, metallic, and covalent. Ionic bonds are way too unstable, while metallic bonds result in repeating structures, crystals, which don't have the chemical variety needed for life. Covalent bonds are really the only option. In these, atoms share electrons with one or more neighbours in order to fill up their outer or valence shells. For example, carbon has 4 valent electrons. It wants 8 for maximum stability. It achieves that stability by connecting to, say, 4 hydrogen atoms and sharing their single electron. This also gives each of those hydrogen atoms 1 more electron to fill up their own valence shells. The result of this arrangement is methane. Now, the cool thing about covalent bonds is that there are countless ways to do this electron sharing, enabling enormous diversity and modularity. For example, if we remove a hydrogen from 2 methane molecules and then stick those together, we have ethane. Now replace one of the hydrogens with an oxygen and we have ethanol. Covalent bonds are the key to the complex and resilient molecular structures needed for life. With this in mind, we can look at the periodic table and rule out all of the elements that form mostly ionic or metallic bonds, which is actually most elements. We're keeping things that are good at forming covalent bonds, even if they also sometimes bond in those other ways. We can also rule out the noble gases since they are barely reactive at all, and the halogens because they're just too much trouble. It's hard to get them to form covalent bonds with more than one element at the same time, and when they react with something it's usually in an explosive manner. Finally, we're going to scrap elements in rows 4 and below. Although these may form covalent bonds, these atoms are so large that the nucleus doesn't hold the electrons with enough strength, leading to dangerously weak molecules. By the way, this is the reason that arsenic is toxic. Cells can accidentally build molecules using arsenic in place of phosphorus due to them having the same number of valence electrons. When that happens, the resulting molecules will break, destroying important structures in the cell or interrupting important processes, and if this happens too much, the cell will die. After making our cuts, we're only left with 7 elements: hydrogen, carbon, nitrogen, oxygen, silicon, phosphorus, and sulfur. Of these, all but silicon are considered fundamental building blocks of life on Earth. Other elements are used by life for very specific functions, but hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur are the most important. And of these, carbon is by far the most critical because it provides the scaffolding of all biochemistry. The reason it's good for this is that it forms strong bonds with itself, and it does so in a variety of ways. In fact, of the 6 building blocks of life, only carbon can form both 1D and 2D structures with itself. In our process of identifying elements that may be useful for life, we got to the 6 main building blocks plus silicon. But why did silicon get dropped by evolution? This seems weird because silicon is chemically similar to carbon, also having 4 valence electrons. Silicon can imitate carbon and form long chains and rings, and the resulting molecules often have similar properties to molecules made with carbon. To give you just one example, we can make silicon oils, and they feel and look just like other kinds of oil. It's the only other element capable of forming complex covalent scaffolds and supporting a large diversity of molecules. Despite all of this, Earth life makes less use of silicon than it does for many of the trace elements like iron. This seems extra strange when you remember that silicon accounts for more than 28% of the mass of Earth's crust. On the other hand, carbon makes up only around 0.02% of the crust. This tells us that carbon must have substantial advantages over silicon. So, let's talk about some of the issues with silicon as a basis for life. One huge one is that silicon-based molecules tend to be far more reactive with water than carbon-based. In fact, although silicon chemistry is extremely diverse, most complex silicon molecules are unstable in water. You can see how this would be a problem for silicon-based life on our very watery Earth. In general, life needs a solvent, a liquid medium that allows molecular machinery to move around and interact. Water is incredible for this. Its thermal stability, power as a solvent, and abundance through the universe make it the best and perhaps even the only decent choice of the base solvent for life. The instability of most silicon molecules in water is actually a huge blow to the viability of silicon-based life. However, water is not our only option. A much greater variety of silicon-based molecules are stable in liquid hydrocarbons, which are present on the moons of the gas giants, and even in sulfuric acid, which is abundant in Venus's atmosphere. Both cases have their issues. Liquid hydrocarbons are cold, which among other things means they have trouble holding in solution the large complex molecules that at least known life relies on. Sulfuric acid is chemically extremely aggressive, perhaps too much for life to get started. On the other hand, xenomorphs are silicon-based and they do have acidic blood. Makes sense that they're silicon in sulfuric acid based. If that's what Venusian life is like, let's cancel the Cloud City construction program before the space horror begins. There is one way to potentially get silicon-based life in water, and that's by coupling silicon with either carbon or oxygen for our scaffolding molecule. Chains of these pairs of atoms can produce some chemical diversity. However, neither case seems to provide significant advantage over just using carbon chains. Another reason that silicon seems implausible as a scaffolding element for life is that the stuff really loves forming bonds with oxygen. Silicon forms stronger bonds with oxygen than with any of the other building blocks of life, and certainly more so than other silicon atoms. Silicon-based molecules are easily broken by oxygen, and silicon-oxygen bonds are hard to break in turn. This means reactions tend to go in one direction when there's oxygen available. And the strength of the silicon-oxygen bond is perhaps the main reason that silicon is rarely used by life on Earth. Although there's an awful lot of it, Earth's silicon is locked up in rocks and it is inaccessible to life. On the other hand, most of Earth's carbon is in CO2 in the atmosphere, which is relatively easily accessible through photosynthesis. There is one sense in which the strength of the silicon-oxygen bond could be useful for life, and that's in energy generation. Let's think about where our energy comes from. It's from the conversion of oxygen molecules which contain a ton of energy in their bonds into CO2 molecules which contain very little. The simplest way to get that energy is to set something on fire, which works great for steam engines but not so great for cells. The mitochondria in our eukaryote cells liberate that energy with a few more chemical steps, finally storing it in the ATP molecule. So, could silicon-based aliens get energy by converting O2 into silicon dioxide? On the surface this looks good because SiO2 is even more stable than CO2, so there's more energy to liberate. The problem is that while CO2 is a gas that can be expelled easily, silicon dioxide is silica. It's sand. It's coarse and rough and it gets everywhere. I hate it. It's not something you want to be building up in your cells or in your lungs. And this wouldn't be a small amount of sand either. A regular person exhales about 1 kilogram of carbon dioxide throughout the day, meaning silicon aliens would need to cough out a good amount of sand, or poop out glass beads or something. Probably there's a way around the issue, but it's certainly not as convenient and energy cheap as exhaling CO2. And with life, any little saving of energy is a big deal. Let's summarize. In certain conditions, silicon potentially has the chemical diversity for an alien biochemistry, but those conditions are pretty specialized and are far less ideal than the ones that support carbon-based life. It seems that if life has the option of using carbon, then it should do so. But it's not impossible that in highly unusual environments, there could be silicon-based life. But what would that life look like? For decades, science fiction authors have imagined silicon-based life as variations of living crystals or rocks. That's because the common form of silicon on Earth is just that. But we carbon-based creatures don't look like walking diamonds or pencil leads, so there's no reason to think of silicon-based aliens looking particularly crystally. Well, actually there is a reason. And that's because living silicon crystals already exist on Earth. Let me present you with diatoms. These are single-celled organisms that have incorporated silicon into their cell walls, making them rigid and basically just silica crystals that encapsulate all the parts of the cell inside them. These beautiful living crystals live simple lives. They just float around on the ocean in long chains, photosynthesizing and producing half of the oxygen that we breathe. Now, to be clear, diatoms are not silicon-based life. It's just that their cell walls are silicon. Everything inside them is based on carbon. But they are at least a proof of concept that one important component of life, the cell wall, can be built from silicon. Okay, so what have we learned? Well, silicon-based aliens are probably slightly overrepresented in fiction compared to their likely frequency out there in the universe. In fact, carbon in water is such an astoundingly good option for biochemistry that there may be no other game in town. Even Carl Sagan called himself a carbon chauvinist for this reason. We'll probably be more similar than different to the alien species of our first contact. But let's not ignore the hydrocarbon lakes of Titan or the acid cloudscapes of Venus, where silicon-based critters may expand our notion of what is possible in the variety of life across space-time. Thank you to Brilliant.org for supporting PBS. Brilliant is an online learning platform for STEM with hands-on interactive lessons. Brilliant is for curious learners, both young and old, professional and inexperienced. Brilliant courses teach you how to think via interactive lessons and problem-solving activities and exercises. For example, Brilliant.org offers a course called Quantum Objects. The principles of quantum mechanics came from investigating microscopic phenomena, the bizarre behavior of quantum objects like atoms and elementary particles that often appear to contradict classical mechanics and probability. In this course, you'll explore experiments of quantum objects and use them to construct new equations of motion, new laws of physics, and a new system of measurement based not on numbers but on algebras. By the end, you'll gain a new appreciation of how the physics of the small enables lasers, transistors, and other modern technologies that define our world. Then you'll be ready to dive into the ongoing revolution of quantum information and computing. To learn more about Brilliant, go to brilliant.org/spacetime. Today we're doing comment responses for the last 2 episodes. There was the one about the new simulations that show how our moon may have formed from a giant impact, done with higher resolution than ever before, and the one on Max Tegmark's mathematical universe hypothesis, which proposes that the most fundamental reality is a Platonic realm of mathematics. We'll start with the latter. One Bronx opines that the basic math of our universe is likely not to be the standard model Lagrangian and the general relativity equations, but rather the principle of stationary action and a specific set of mutually consistent symmetries. Well, I absolutely agree, and certainly agree on the core point, which is that if the mathematical universe hypothesis is true, a given universe probably shouldn't be defined by the Platonic existence of a complicated set of equations, but rather a very simple set of rules. In the mathematical universe hypothesis, the physical world is emergent from a more fundamental mathematical world. But that doesn't mean that complex mathematical structures can't also be emergent from simpler, more fundamental mathematical structures. Esley Odegaard mentions that we should have included Sir Roger Penrose's 3 worlds ontology, in which reality is described as 3 realms of existence, each emerging from the other. Now, I agree, and this was totally going to be in the episode, but we ran out of space for it. To give you an overview, Penrose proposes this way of thinking about the circular emergence of reality. We have the material world as emerging from a Platonic mathematical world, in the sense that without the possibility of mathematical regularities, our material world couldn't exist. And then the mental world emerges from the material in the sense that our material brains generate the mind. And finally, the Platonic world emerges from the mental in the sense that minds are able to conceive of the full language of mathematics even beyond its manifestation in the physical. This is pretty different from Tegmark's idea that the Platonic math world is the ontological precursor to everything else. Penrose doesn't grant primacy to the Platonic, which is why I ultimately decided to leave this out. Perhaps it's for a future episode. If anyone wants to read about this, get Penrose's book Road to Reality. But fair warning, reading it is a full semester intensive physics course, which, by the way, is a recommendation. Okay, now on to the far less abstract idea that the moon formed when a planet that we named Theia smashed into the newly formed Earth. Mark Central mentioned an idea that I've never heard before, the idea that lumps of relatively intact Theia material may still be present in the Earth's mantle. There are these high-density blobs of matter that sit at the boundary between Earth's mantle and core, called large low-shear velocity provinces. Some scientists have suggested that this is material from the planet that collided with Earth in the moon's formation. There is some loose evidence for this. For example, isotopic ratios in basalt thought to be from lava plumes rising from the regions above these LLSVPs have primitive isotopic ratios consistent with material that wasn't mixed in the giant impact. It's a very cool possibility, though obviously a lot more work is needed. Alice asks, if the moon is a very unlikely event, and an unusually strong iron core is necessary to protect the development of life, does this provide a sufficiently hard filter to resolve the Fermi paradox? Well, the answer is we don't know, but people have speculated that this might be the case. My personal intuition is that the extremely hard filter needed to explain the Fermi paradox is actually a chain of just somewhat hard filters, and our large moon may be one of those. Other potential filters include having a solar system composition like ours, so large protective gas giants in the outer solar system, but only small terrestrial planets in close, and say a star of a very particular quality, and so on. Check out our video on the rare earth hypothesis for more on this. I'd like to address a comment about my comment response from the Supercritical Fluids episode, where I joked that there are animals with hands large enough to swim in gas, and they're called birds. Several people noted that bats would have been a better example because, well, as Zovo notes, and I quote, "Bat wings are formed from the membranous extensions from palm to fingertip between the digits 2 through 5. Bird hands are actually very small and have completely fused together into a structure called the carpometacarpus, tipped by greatly reduced digits 2 and 3, digit 1 bearing the ulula anterior to the rest of the carpometacarpus. Birds just have very long feathers to form their flight surface." Well, thanks for that, Zovo. So I've learned a lot from my mistake, both regarding the size of flighted animal hands, and that even casual jokes should be subject to rigorous research and fact-checking. My sincerest apologies to everyone. Several people also noticed that I flubbed when naming Neptune's moon Triton. I misspoke and said Titan, which is of course Saturn's moon. Thanks to those in the comments who wondered if it might just be my Australian accent, like we don't pronounce R's after T's or something. Yeah, that's totally it. Just remember, anytime you hear me misspeak, it's actually just how Aussies pronounce the actual correct word. Also, all Australian birds have gigantic hands, unlike everywhere else in the world.